All right, so welcome to Differential Equations. And for many of you, I've been your professor for, some say Calc 1 onward. For others, I've maybe even pre-Calc onward. But nevertheless, you're here, you've done it. You have, for many of you, you have reached the last math course that you will need for your major, right? So many of my engineer students, this is the pinnacle, right? The last of the last. Now, I do have an entire semester to talk you out of majoring in these fields such as mechanical, electrical engineering, and potentially get you to follow me into the area of mathematics, all right, the truth. But nevertheless, I want to say a couple quick comments. So, the class, I mean, obviously it goes without stating, the classes can be demanding. You do need to find a way to get some practice in. Unfortunately, unlike, say, if you had me for Calc 1, 2, or 3, that finding resources to help you study at this level of mathematics starts to get a little hard, right? It starts being getting a little bit scarce out there. In addition, the Larson calculus book had a beautiful feature where you could go to CalcChat, and if you were working out some homework questions, and you could see the detailed step-by-step solution process, right? The student solution manual. Finding resources like that are going to be tough for classes like this. That being said, if you do come across resources, why don't you post them in our Discord, right? Our differential equations Discord, because you know what, maybe some of your colleagues can post their resources as well, and it'll just help everyone grow. In terms of the content of the course, right? So lecture-wise, the lecture content, given that we're still doing this online, the class will follow the same structure as say Calculus 2, if you had me, or Calculus 1 or Calculus 3, the same structure, where the videos will be pre-recorded and posted. And I won't go into any more details because that'll all be found in the syllabus. In terms of content, so what you're going to find is many times it's going to seem like we've glossed over some of the finer details of these differential equation techniques. And in fact, we have, because it hasn't been very long that differential equations was, it was mostly graduate work and, doctorate work and postdoctorate work. But now, it's been pushed down into the undergraduate world. And then because of how unbelievably useful these techniques are, it's even being pushed farther down into sophomore year of college, right? So all that to say that in due reality, I don't know when I was a sophomore if I would have had, I don't think I would have had the level of rigor to really understand these differential equation techniques that I will be teaching you. But this is the world that we live in, and we are going to do our best. Okay. So no more. If you don't know me, shame on you. But if I have never had you before, welcome. So I'm your professor, Professor Dyke. I teach full-time mathematics here on the Fauquier campus. And other than that, I'm not very interesting. I have my wife and my kids and my dogs, and I do own a business in a computer and electronic recycling company, or in warehouses in Winchester, and I play video games and play board games, and no more about me. That's not very interesting. Ready? Let us jump into differential equations. So let's chat about the way the types of differential equations, right? And so henceforward, I'm gonna write DE for differential equation. So normally, like when you have these differential equations, we try to classify them, and so the classifications could be that they are ordinary differential equations or partial differential equations. We might further classify them into linear or non-linear differential equations, or homogeneous or inhomogeneous differential equations. And in fact, what you'll see is that a certain equation will have multiple of these titles, right? So it might be a second order ordinary linear differential equations. So like there's different ways of classifying them. Now another way we classify is by the order of the differential equation. So if I'll just make up something really quickly. So if you had the following, you can see that in terms of the derivative, the highest derivative that we have in this equation is y prime, right? So this would be a first order differential equation. If you had y double prime, this would be a second order differential equation. So a lot of times we classify by the highest derivative. Now, next thing that we want to chat about is, well, let's assume that you do solve one of these differential equations. How do we express the solutions? Well, one way of expressing, you can have what we call the general form of the solution is I will unpack this in just a second, but you can just imagine that you have a function. Basically it's set equal to 0, right? And notice that the function is both a function of x and y, and as well as the derivatives, right? So it could be y prime, y double prime, all the way up to, I put to the power of n, right? And this n represents the highest derivative that the function has. So notice that it's a function of quite a lot of inputs here. So another way of expressing a solution is to solve for the highest derivative. So if the highest derivative in your equation is a second derivative, you could solve for the second derivative, and that would be a way of expressing your solutions. Now, in terms, the next type of where we want to go next is the type of solution could be defined as an explicit solution or an implicit solution. We'll start with the explicit solution. So the way we want to think about this is I will do my best to read. I will read the definition, the formal definition, and then I'll try to give you an in other words of what this is saying. So what you have is you have some function. Don't worry about the notation yet, right? So you simply have a function that when substituted for y now it says equation 1 or 2. Basically what they're saying is when you substitute for y in these equations, satisfies the equation for all x in some interval I. If that's the case, what you have is referred to as an explicit solution. to the equation on I. So the idea, like, in other words, when you have a differential equation, what do you have? You have an equation with some type of derivative in it, right? So here is a differential equation, right? So we have an equation with a derivative in it. So to solve it, right? Can you imagine if you want to solve a differential equation? Well, wait a minute. Isn't that what we did if you wanted to integrate, right? Think about the process of integration. We had the derivative, and we were integrating to get back to that original function, right? That original function that you took the derivative of. Well, that would be the solution or a solution to the differential equation. So do you see what I'm talking about? So when we were integrating, we were attempting to solve differential equations. So the key word here is all of x in the interval I. So what that means is when you do substitute, you get, like, so for example, you have a proposed solution to a differential equation. You want to check it, right? We want to check to see if it works. When you substitute, it has to satisfy the equation for all x in the interval. And now, let's just jump right in. So notice for this first section, we're going to be, we don't have to roll up our sleeves. We are given a proposed solution. Right? We're given the solution. We want to see if it actually is a solution. And later we're going to see, is it an explicit or an implicit solution? So our job is to show that the following function, right? So you can imagine like you just got done integrating and this is what you got. Okay? So we want to show that the following function is an explicit solution to this linear differential equation. Now, after we get done with that, we want to show that this function is not a solution, explicit solution to this differential equation. So let's go ahead and, just for notation, and this is just a second derivative. We'll make the notation a little bit easier. We'll just use y prime and y double prime. So let me go ahead and rewrite this guy. So I'm gonna kind of bring this over here. So let's rewrite this to be y double prime minus 2 over x squared y is equal to 0, right? So that might be a little bit easier to digest. And again, now our job is to show that this function is a solution to this differential equation. Okay. Now, the way we can do that is we can simply substitute, right? Life is easy when you start with the answer, right? We didn't have to do any work to get this answer, this solution. But we want to double check that that we're going about it the right way. So we want to be able to substitute in to this differential equation, and we want to make sure that that the equation balances for all x in the interval. So let's take a look. So the highest derivative in this equation is a second derivative, right? So we're going to need f prime of x in order to get to f double prime of x. So let's go ahead and take those that first and second derivative really quickly. So f prime of x, well, that's just going to be 2x, what is that? It's going to be negative, so that's plus x to the negative 2. Let's take one more derivative. So f double prime. Let's see if I can make that a little bit better. So f double prime of x. So So one more derivative, that's just going to be 2, and now it's going to be minus 2x to the negative 3. All right, and if you follow me, what's going to happen is we're going to be subbing this in for y, and we're going to be subbing this in for y double prime. And we hope that everything balances, right? So let's go ahead and I'll draw you some arrows here. So we're going to be subbing in for y here. We're going to be subbing in for y double prime here. And let's go ahead and do that. So that's going to be 2 minus 2x to the negative 3. And that's going to be minus 2 over x squared. And now let's plug in for y, so that's going to be x squared minus x to the negative 1. And that's supposed to equal 0. So let's see what happens. So we gotta, obviously we're going to have to, distribute a little bit and see what happens. So let's distribute that 2 over x squared. So I got 2 minus 2x to the negative 3. All right, so if I distribute here, what am I left with? I'm just left with 2, right? Or I'll just, you'll see what I'm going to do in just a second. And then I got to distribute here as well. And that's not bad. So that's negative 2 over x squared, and that will be multiplied by, well, x to the negative 1 is just 1 over x. So you can see how that's going to be x cubed. So when we distribute, we're going to get minus, okay, and we'll leave that minus symbol up front. So that's going to be 2 minus 2x to the negative 3 equals 0. Okay, well, you see what happens if you drop those parentheses, right? We're going to, when all is said and done, we're going to have 2 minus 2x to the negative 3 minus 2 plus 2x to the negative 3 equals 0. So we end up with a true statement, right? And this is a true statement from negative infinity to 0, all the way from and then from 0 to infinity. Not at 0, right? We can't. I mean, if you look at your original equation, 0 is not within the domain. So if it's 0 is not within the domain of the differential equation, all we need to do is make sure our solution works for all x in the interval, right? So whatever, either the interval is stated explicitly or the interval can be that of the domain of the function. So not bad, right? Take some derivatives, plug them in. So what I'm going to do right now is erase. Well, I'll tell you what, I might be able to do this above. So now let's look at f of x equals x cubed. Let's go ahead and take our derivatives. All right, so that's 3x squared, and that's 6x. Let me go ahead and write that differential equation. So what was it? Y double prime minus 2 over x squared, y equals 0. And now we're going to do the same thing. We're going to be plugging x cubed in for y, and we're going to be plugging 6x in for y double prime. And let's see what we have. So we would have 6x minus 2 over x squared multiplied by x cubed equals 0. And so first off, if you once you multiply this out, what will you be left with? Well, x squared will cancel x squared here. You'll be left with 1x. So this will end up being, let me see if I can scoot this around a little bit. So after you distribute, you'll be left with 6x minus 2x equals 0, or in other words, 4x equals 0, which now this, so first off, this equation is only valid, right? This equation is only valid when x is equal to 0. That is not within the interval I, and not only that, but 0 is restricted from that as well. So this doesn't work. X. So if you had x cubed, that is not a solution. My sincere apologies. Yeah, if you had if you had x cubed, that is not a solution to this differential equation. Okay. Be careful, don't get lost. In other words, you would never integrate this and get to x cubed. Okay. Let's keep going here. So the way we're going to get good at this, we're gonna follow the same pattern, right? Where we're gonna substitute in to the differential equation, see if everything balances. But let's take a look at when things are not so easy, like when things are not expressed explicitly, right? So for example, we want to show that for any constants C1, C2 that we choose, we can choose any constants we want for any of the constants C1 and C2 that we choose. We want to show that this function is an explicit solution to this differential equation. One more time. We want to show that this function is a solution to this differential equation no matter what we pick for our constants. All right. So let's get back to it. So f of x is given to us. Right? So that's c sub 1 e to the negative x plus c sub 2 e to the, 2x. Now, taking a look at our differential equation, we got a second derivative, a first derivative, so we're going to need f prime and f double prime. Okay, so let's go through and let's take these derivatives with respect to x, and this is, at this stage, I'm fairly positive you know how to take the derivatives of, e to the e to the u type problems. So this would be, let me make sure I don't make any silly mistakes. That would be negative c sub 1 e to the negative x. Right, so because u, yep, so, and then that would be plus derivative of 2x is 2, so that would be plus 2 c sub 2 e to the 2x. Okay, so let's take one more derivative. So now we would be back to a positive c sub 1 e to the negative x plus, and this time it would be 2 and 2 is 4, so 4 c sub 2 e to the 2x. Okay, and at this stage, although this is, I agree with you, this is slightly tedious, we need to substitute, right? So we got to substitute in for y prime, y double prime, as well as substitute in for y. Let me see if I can entertain yourself for just a second. Let me see if I can capture all of that. So c sub 1 e to the negative x plus 4 c sub 2 e to the 2x minus, right, and then minus what? Minus negative c sub 1 e to the negative x plus 2 c sub 2 e to the 2x minus, now it's 2 times y, so that's 2 times c sub 1. Let me do this. Let's cut that and paste it so I can write a little bit smaller. So 2 times y, so that's 2 times c sub 1 e to the negative x plus c sub 2 e to the 2x. And that's got to get us to 0. All right. So what I'm going to do is I'm going to distribute here, and then I'm going to drop these parentheses and regroup. So I want, in other words, after I drop the parentheses, anything with an e to the negative, any term with e to the negative x's, I want those to be in one group. And the terms with e to the 2x's are going to be in a group. So what does that look like? Well, that would be, again, entertain yourself. I'm going to take my time. So that's c sub 1 e to the negative x. What other e to the negative x's do we have? So let's just make sure we change our signs. So that's plus c sub 1 e. Yeah. So I think what I said is correct. Yeah. So let me just. I was going to try to re-explain it, but there's no need to re-explain it if what I said is correct. So I got a c sub 1 e to the negative x, and then I would have a negative 2 c sub 1 e to the negative x. So the classification is what I should have said is because we want to be able to have our c sub 1's left, and we're going to be factoring out an e to the negative x. So that's what I want to make sure. So we're kind of bunching our e to the negative x's, or grouping them so that we can factor out the e to the negative x. Now all I want to do is make sure I haven't done anything silly. See someone. Okay, so that looks good, I think. And now let's go ahead and let's see if I have enough room to group the rest of these. So 4 c sub 2 e to the 2x minus 2 c sub 2 e to the 2x minus 2 c sub 2 e to the 2x. Okay. So, unless I've made some type of translation error, then let's go ahead and proceed. So, I'm going to be factoring out an e to the negative x from each of these. You'll see why. So, if I factor out an e to the negative x, I would have c sub 1 plus c sub 1 minus 2 c sub 1. then I want to factor in e to the 2x out of the next group. And I would be left with 4c sub 2 minus 2c sub 2 minus 2c sub 2. And now you're going to see why those, remember, constants, C1, C2, any choice of our constants would not play a role in our solution. And you can see that because no matter what you choose for C sub 1, do you see how this is all going to just zero out? C sub 1 plus C sub 1 minus 2C sub 1. This just ends up being e to the x times 0. Forgive me. So no matter what you choose for C sub 1, it's going to zero out anyway. Plus e to the 2x. Again, 4 minus 2 is also 0. So for all C sub 1, C sub 2 on the interval, and the interval here is negative infinity to positive infinity. For all C sub 1 and C sub 2, you have an explicit solution. So those constants are not contributing there. Okay, so the majority of the time, explicit solutions like this, right, are not possible. A lot of the times we end up with solutions, what we call implicit solutions. To make sure, before we get started, just to make sure you understand what I mean. So y equals 2x plus 1 is an explicit equation, right? You were able to solve for y. Whereas y minus 2x equals 1 is an implicitly defined equation, right? So this is an explicitly defined equation. This is an implicitly defined equation. Now, so for example 3, we want to look at implicit solutions, and so let's kind of take a look at our definition. So basically, some relation, right? Some equation here, g of xy equals 0. We can say that it that is an implicit solution of a differential equation on some interval. And here it is, if it defines one or more explicit solutions on that interval. I'll see if I can give you an in other words in just a second, but let's take a look at example 3 and how we would have to approach this differently from the previous two examples. So notice that the question is the same. We want to show that this equation, this relation, right? It might not be a function, but we want to show that this is a solution to this differential equation. Except you could solve for y, you could solve for x, you could go about taking the derivatives and plugging them in. But we are simply interested in showing that it defines a solution along this interval. So in this case, this is an easy scenario because we actually can solve, although that's implicit, we actually can solve that for y. All right, so if we wanted to solve for y, we would move everything else to the right side of the equation and then take the square root. So we would have y is equal to plus or minus the square root of x cubed minus 8. Now, we'll just for now, we'll just focus on the principal square root. We'll just the positive one. But this will work for both the positive and the negative. So what we're going to do is we're going to let f of x equal the square root of x cubed minus 8. All right, so we're going to define a relation here, a function here. And now notice that our differential equation is solved for its highest derivative. Right? Let me write it. So we'll just rewrite this as dy dx. So that's just y prime is equal to 3x squared over 2y. So now we were able to, this is already solved for y, for the derivative. So when we substitute, all we need to do is substitute in for y. And then we have a derivative that is, my apologies, my phone is going off. So then we have a derivative that is, as soon as we substitute in, we have a derivative that is defined in terms of x, right? So let me go ahead and substitute. Let's see what that looks like. And while I'm thinking about it, let me turn my phone off so I don't have any more disruptions. So let's go ahead and substitute. So y prime is equal to 3x squared over 2 times the square root of x cubed minus 8. Okay. Notice that both f of x and dy dx, both of these are defined over the interval 2 to infinity. Does that make sense? Right, so in other words, I can choose any number I want in this interval. For example, 3. I could plug 3 in for x into this function. No problem, it's defined. I could plug 3 in for x into this differential equation. No problem, it would be defined. So it is defined everywhere throughout this interval. So we are good. This would be considered an implicit solution. Okay, so let's go ahead and see if we can do another example. So same idea. We want to show that the following relation is an implicit solution to this differential equation. And how do we go about that? Well, let's agree that this is not as easy, right, to solve for y. Right, so we're unable to solve for y in terms of x. So we're gonna have to take the derivative the way it sits. So let's go ahead and let me write that. So let's just say f of x is equal to x plus y plus e to the xy. And let's go ahead and look at our differential equation. So I'll rewrite this using the y prime notation. So I have 1 plus x e to the xy times y prime plus 1 plus y e to the xy equals 0. Okay. So remember, we're going to be subbing in for y and y prime. All right. So let's go ahead and take some derivatives first before we start subbing. So let's find f prime of x. So we only need one derivative. We don't need two. So let's go ahead and take f prime. So we're going to take the derivative of f with respect to x. So that's going to be 1 plus y prime plus. All right, and now we got we got a product and a chain here, right? So if we want to take the derivative with respect to x of e to the xy, well, I can't assume that you have a understanding of partial derivatives, right? The calculus 3 is not a prerequisite, odd enough, for differential equations. So let's just go ahead and take the derivative the way we would have done in Calc 2, for example. So let's let f be defined as x. Let's let g be defined as y. F prime is going to be equal to 1. G prime is going to be equal to y prime. And now let's go ahead and let's go ahead and form our product. All right, so that's going to be f prime g plus f g prime. So we're going to end up with 1 times y plus x times y prime. Right, and we also have that chain rule for e to the u. So remember, just really quickly, the derivative of e to the u, in case it's been a while, is simply e to the u times du dx. So that should give us, so we got y, yeah. So that's going to be, so in other words, I know I'm talking to myself as I talk to you. So just remember, if you're taking the derivative of this is an e to the u. So you're basically saying let u equal xy. Now, when you go to take u prime, right, that's when you are going to need a product. So it's going to be e to the u times u prime is what it comes down to. So this is going to be e to the xy multiplied by y plus x y prime. All right, a lot of work to get to this result, but this is going to be going right here. Okay. So what do we do now? So remember, we're gonna want to substitute. So we're gonna want to substitute f and f prime. We want to substitute that into our derivative, and we want to make sure that that it balances. We want it, so let's see if you can follow me here. I'm trying to think if there's a few ways we could do this. Let's go ahead and distribute here before we do anything. Let's distribute here and here. See if you like this approach. So if I distribute, I'd have 1 plus y prime. Okay, plus, well, y times e to the xy. Plus, what do we got? X e to the xy times y prime. Okay, so we distributed. Now, let's see if we can group, right? So let's group any of the derivatives, any terms with derivatives. Let's group them together, and then let's group. And what I'll do, if you don't mind, the y primes are helpful, but they also can make things cluttered, right? So it's hard to notice the little prime symbols, especially with this stylus. So these are still y primes. I'm going to use dy dx notation. So that being said, let's group any terms with dy dx's in them together. So that's going to be, let's dy dx, and then let's plus x e to the xy dy dx. You'll see where I'm going. Just entertain yourself. All I'm doing is moving this guy over here, right? I'm grouping these two together. And then let's go ahead and group what's left over together. So that's plus 1. We'll do it in order. So plus y e to the xy plus 1. Okay. Now let's factor out a dy dx. So if I factor out a dy dx here, I would be left with 1 plus x e to the xy plus y e to the xy plus 1. And wait, stop. Does this look familiar? Yeah, this should look familiar, right? This is the differential equation, right? So that through the substituting, we were able to you can see these guys are identical when n equal to 0. So at that stage, you were able to show that that this is an implicit solution to this differential equation. Do you see the manipulation, right? I mean, it is more the same. You're just taking derivatives and subbing in, but sometimes you got to have a game plan with where you want to stop, right? So we can stop at this point right here. Okay, now the only thing obviously there is more to this. As an aside, right there. So there's some advanced theorems. I believe it's called the implicit function theorem, that guarantees this is an implicit solution over the interval. But again, beyond the scope of this class. Okay, so I think it's about time to take a break. And then when we get back, we have discussed we've discussed some scenarios where you've been given the solution. You're kind of just checking to see if it actually is a solution. But where we're going to go next is we're going to talk a little bit more about instead of finding a general solution, right? One of many. We want to find the actual solution, the particular solution. In other words, remember all the plus C's, right, that we would have in calculus? We actually want to start looking at how do we actually find out what the value of C is, so you don't have an infinite amount of solutions. But I will see you in the next video.